Welcome back to Halogenoalkanes, and in this video we are going to continue on looking at nucleophilic substitution, looking particularly at the hydrolysis of halogenoalkanes, the reaction with aqueous hydroxide ions. But just before we do that, let's do a quick recap of what nucleophilic substitution is. So we're talking about the reaction of halogenoalkanes, which are carbon chains with at least one halogen atom in them, connected to one of the carbon atoms. That results in a polar bond being set up between the carbon and the halogen. The carbon is less electronegative, so will be slightly positive, and the halogen is more electronegative, so is slightly negative. This leaves a halogenoalkane prone to attack by a nucleophile, and will use the standard symbol Nu, and we'll give it a negative charge, although a nucleophile does not have to have a negative charge, but it must have a lone pair of electrons that it can use to donate towards the carbon bond, the carbon atom, to form a bond with it. So that's exactly what happens. It uses its lone pair of electrons to form a bond with a carbon atom. As a result, carbon cannot have 5 bonds, and so the carbon-halogen bond breaks with that pair of electrons in that bond going to the halogen atom, and it then leaves as a halide ion. So as a result, what we produce is the substituted product of the nucleophile replacing the halogen, and the halide ion leaves with a lone pair of electrons now. So that is nucleophilic substitution, and let's look at a hydrolysis reaction. So the last example of nucleophilic addition of halogenoalkanes that we're going to look at is the reaction of a halogenoalkane with hydroxide ions. Hydroxide ions are OH minus. And the oxygen has a lone pair of electrons, actually has 3 lone pairs of electrons, but we'll just show one of them there. So it can act as a nucleophile. But this particular nucleophilic substitution reaction can also be given another name. It can be given the name hydrolysis. It's a particular type of reaction that we can classify as hydrolysis. And as a result, we're going to produce the corresponding alcohol. So what is a hydrolysis? Well, let's think of that word hydrolysis. The hydro part means water, and the lysis part means to break up. So we're literally breaking up molecules by reacting with water. So when the molecule breaks up, one part of the molecule will bond with the hydrogen atom of water, and one will bond with the OH part of water. So if you think of water as being H2O, one part of our broken up molecule will be with the H, and one will be with the OH. And so we can write hydrolysis reactions as the reaction of a molecule with water. So you can see here the reaction of bromoethane with water, and you can see that the halogenoalkane molecule has broken up, so we're just left with the bromine atom having separated off, and the ethyl chain separating too. And you can see in terms of how that then bonds with the water, how the water breaks it up. You can see that the ethyl part of the molecule bonds with the OH from water, and the Br bonds with the H from water. So you can see there that water has broken up this molecule, so it's no longer C2H5Br. That Br has broken off, it's gone off with the H from water, and the ethyl chain has gone on with the OH, and that produces the alcohol. That's actually the formula for ethanol. Now with hydrolysis, we can catalyse it with either an acid or an alkali, and the alkaline hydrolysis is where we're going to talk about our nucleophilic substitution. So if it was acid hydrolysis, we normally just heat the substance to be hydrolysed with dilute mineral acid, such as hydrochloric acid, sulfuric acid, nitric acid, or whatever. The reaction's heated under reflux. And it's written, the equation is normally written as your reaction with water, but with the H plus ion written just above the arrow to show that it's a catalyst. It's not actually used up in the reaction, so therefore it can be written on the arrow. But we're going to be focusing here on the alkaline hydrolysis. So what that normally involves is heating the substance to be hydrolyzed, so a halogenoalkane in this case, with dilute alkali, so something like sodium hydroxide or potassium hydroxide. This time, rather than writing the hydroxide ions, say for example on the arrow, we get slightly different products here. We will get the sodium or the potassium salt, depending on what hydroxide we use. So this time the reaction is actually written as the reaction of your halogenoalkane with the hydroxide itself. So here it's written with sodium hydroxide. And you can see that OH group goes on to the halogenoalkane, and that's where we'll see our nucleophilic substitution, the hydroxide ion acting as the nucleophile and kicking out the bromide ion. And then you can see the product, the side product is your sodium salt, so in this case sodium bromide. Or it's sometimes written just simply as the hydroxide ion reacting with your halogenoalkane, again giving your corresponding alcohol, and then just your Br- ion being kicked out. So what's the mechanism going to look like? Well, with this is where we're going to introduce the idea of SN1 and SN2 nucleophilic substitution mechanisms. Essentially, they all proceed by nucleophilic substitution, so that mechanism on the whole is the same as what we've looked at before, but things happen in a slightly different way, maybe a slightly different order, and we consider them as slightly different mechanisms, and that depends on the structure of the halogenoalkane. But overall, this is how our reaction proceeds. This is not a mechanism, this is just essentially a structural equation. But what you can see is we start with our halogenoalkane. I've just given the example of bromoethane. And it reacts with our hydroxide ion, the hydroxide ion acting as the nucleophile. And as a result, the hydroxide ion has replaced the bromide ion in the halogenoalkane. And so as a result, we produce the corresponding alcohol. So an OH group connected to a carbon chain. I know we've yet to look at that topic yet, but that is what an alcohol is. You would have met that at GCSE. So we produce the corresponding alcohol. In this case, it's ethanol, and the bromide ion is kicked out of the molecule. And in reality, we would be reacting with something like sodium hydroxide. So the bromide product would be sodium bromide. But what we want to do now is have a look at the particular mechanism by which this proceeds. And as I said, that depends on the structure of the halogenoalkane. So let's look first of all at the hydrolysis of primary halogenoalkanes. Let's just have a quick reminder of what a primary halogenoalkane is. It's one which has one carbon atom directly bonded to the carbon atom that is bonded to the halogen. So let's draw the structure of the one that we have and show how that's a primary halogenoalkane to show you that structure. So again, we have bromoethane here. So if we look at where our halogen is, what we then want to do is essentially highlight the carbon that it's attached to and see from there how many carbons is that carbon attached to. So you can see here it's connected to one carbon and one carbon only, and that makes it a primary halogenoalkane. So the structure of a halogenoalkane is really based on, well, how many carbon atoms is the carbon that the halogen attached to. So look at the carbon that the halogen is attached to. How many carbons is it attached to itself? So you can see here bromoethane only attached to one carbon. That makes it a primary halogenoalkane. And what we see is that this particular nucleophilic substitution is one called SN2. Where do we get this idea of SN2 from? Well, it's a capital S, a subscript capital N, and then a 2. So that's a capital S, subscript capital N, and then a big 2. Where does that come from? Well, the S is for substitution. The N is for nucleophilic. And the 2 is for bimolecular. What we mean by that is 2 molecules. Bi means 2. And molecular, obviously molecules. So what that means is that this mechanism proceeds in such a way that the rate determining step depends on 2 molecules. So let's have a look at the mechanism and we'll explain that as we go along. So let's have a look at what happens at the first stage of the mechanism. I'm going to draw the shape of our halogenoalkane slightly differently so we can see more true shape around our carbon atom. So don't draw it this way, and don't draw this into your notes. But what we're going to do is we're going to take this central carbon as such, the one that's attached to our halogen, and we're going to show the 4 different groups around it in a tetrahedral shape. Because remember, carbon has a tetrahedral shape because it has 4 bonding pairs of electrons around it. So if you see the 4 groups, that it's attached to a bromine group, a hydrogen, another hydrogen, and a methyl. So don't draw that in, but let's convert that into a tetrahedral shape, and we're going to kind of draw it sideways as well. So just so you can see where that comes from. So there's your central carbon, and we'll draw the bromine group that it's attached to. And then we'll draw one hydrogen, doesn't really matter what way you draw this, down that way, and then our wedged bond to show this coming out of the page as such, we'll make that our other hydrogen, and then our dashed bond will make that our methyl group. So see at the end here, this is the CH3 group, so we'll represent it that way. So hopefully that makes sense, just converting our kind of standard structural formula to a shape that better reflects the true shape around that carbon atom. What we also need to show on our carbon-bromine bond is our delta charges. So remember, carbon is delta positive, bromine is delta negative. And then what we'll draw is our nucleophile, which is our hydroxide ion. So I'm just going to draw it kind of backwards to show the lone pair ready to attack our carbon atom, and that will have a negative charge on it, OH minus. So what we see at this stage is something very similar to what we've shown before in our mechanisms for nucleophilic substitution. We see that the hydroxide ion uses its lone pair of electrons to form a bond with the carbon, and as a result, carbon can't have 5 bonds, so this carbon-bromine bond breaks, and we show that using a curly arrow going towards our bromide ion. So it's going to essentially escape with the pair of electrons. So you can see there's 2 things happening here. The hydroxide ion is using its lone pair of electrons to form a bond with the carbon, and then the carbon-bromine bond is breaking. That happens simultaneously, and what it does is it generates a transition state where the hydroxide ion is moving in and the bromide ion is moving out. So let's draw the transition state at stage 2. So if we draw, first of all, our central carbon, and then we'll draw our hydrogens and methyl group. So if we start to show this hydrogen and methyl group up more towards near the top, so the way I've represented it here, the hydrogen would be coming out towards us, and the methyl group would be going back into the page. And we'll draw the other hydrogen straight down like this. So this is more, at the minute, like a trigonal planar arrangement, because what we'll see as the nucleophile comes in, it's going to push those bonds kind of in the other direction, facing the opposite way. Let's then draw our nucleophile coming in, and how we represent this transition state is by dashed lines coming in from the nucleophile. So what this is representing is that the nucleophile is coming in and forming a bond with the carbon. If you can imagine it, don't draw this red arrow in, but it's like that bond is forming and that hydroxide ion is moving closer and closer in towards the carbon. So we'll just take that away for now because you don't include that in your diagram. What then is happening as a result is the bromine bond is breaking, so it's lengthening, it's getting longer, and that bond is breaking. So in essence, if we were to show that with an arrow, it's moving its way out, but again, don't draw that. So it's like this nucleophile is coming in and the bromide ion is on its way out, but we don't represent that in the diagram. So the OH, the bond to the OH group is shortening, the bond to the bromide ion is lengthening because it's on its way out. And we need to show the charge, and we show that overall by putting square brackets around this molecule. This is our transition state. As our hydroxide ion comes in, our bromide ion is on the way out, and overall the charge is minus. And that's again balanced with the charge at stage 1. Remember, in a mechanism, the charges must balance at each stage. So this is the slow step where the hydroxide ion is coming in and the bromide ion is leaving. That's the slow step. It's also called the transition state. And so this slow step, the rate determining step, the slowest step in a reaction mechanism is called the rate determining step, because the slowest step will be the one that holds you back, essentially, that prevents the reaction from going any faster. So it's called the rate determining step. And because both of our molecules are involved in the rate determining step, so both our nucleophile, our hydroxide ion, and also the starting molecule, the starting halogenoalkane, are involved in this transition state, this rate determining step, then this is why it's called an SN2 reaction, because the rate determining step involves two molecules, the nucleophile and the halogenoalkane. So when the hydroxide ion fully comes in and the bromide ion fully comes out, then we are at stage 3, which is essentially our final molecule. Let's draw our original bonds first of all. This time we can see that the methyl group and the hydrogen are facing the opposite direction to what they were in the original halogenoalkane. But you can see we've stuck with dashed for the methyl group and the wedge for the hydrogen atom. It's just like those have been kind of pushed back as the hydroxide ion has come in from the opposite end. And then our hydrogen will now be a slight diagonal to the right. Again, that was originally a diagonal to the left, but it's now to the right as the hydroxide ion has come in. And let's just then draw our hydroxide ion in here. That has come in, and ultimately that bond has been formed by the lone pair of electrons that was on the hydroxide ion nucleophile to start with. What else do we have? We have our bromide ion, which is our leaving group. It has left with that pair of electrons that was originally in the carbon-bromine bond. So here is our mechanism for primary halogenoalkanes reacting with hydroxide ions acting as nucleophiles. This reaction is a hydrolysis reaction. We're breaking up a molecule with water technically, but we show it as the reaction with the hydroxide ion. The bromide ion then could be seen as reacting with the H+ ion from the water, but because we'll use sodium hydroxide, it'll actually really be NaBr that will form rather than hydrogen bromide. So this particular type of nucleophilic substitution mechanism is called an SN2 mechanism. It's called that because S comes from substitution, N comes from nucleophilic, but the 2 comes from the fact that there's 2 molecules involved in the rate determining step, which is stage 2, and both our nucleophile and our halogenoalkane are involved in that rate determining step. So it says here, the rate determining step depends on the concentration of both the halogenoalkane and the hydroxide ion, and you'll do a little bit more work on rates next year. But for now, just know that both of those molecules are involved in the rate determining step, which is why it's called SN2. They can be viewed as single step mechanisms because this bond forming and bond breaking, the bond forming of the carbon to the hydroxide ion and the bond breaking of the carbon to the bromide, they happen simultaneously. You may want to write that beside the single step mechanism or even in the space that you have in the corner. So as we said, again, I'll show this with arrows, but don't add this to your diagram. So as the hydroxide ion comes in and that bond forms, it will shorten as the bond is formed. And as a result, the bromine is kicked out and that bond will lengthen and it will break. And that process happens simultaneously. As the hydroxide ion comes in, the bromide ion simultaneously leaves. So that's an SN2 mechanism, and that applies to primary halogenoalkanes, and you need to be able to draw that particular mechanism. So maybe get a blank page, try and draw it for yourself, study it and see if you can do it from memory. And then what we'll do is we will have a look at the hydrolysis of tertiary halogenoalkanes, so halogenoalkanes with a different structure, and see how that varies with them. So over on page 23, let's have a look at the hydrolysis of tertiary halogenoalkanes. So remember, the CA definition of a tertiary halogenoalkane is a halogenoalkane which has 3 carbon atoms directly bonded to the carbon atom that is bonded to the halogen. Let's draw the structure of the halogenoalkane that we have here in this equation. The molecule is called 2-bromo-2-methylpropane, and there's actually, I'm just spotting there's a little dash missing after that too. There should always be a dash between numbers and words or letters in a name of a molecule. But if we have a little look at the carbon that's attached to the halogen, so it's that carbon there. How you work out the structure of a halogenoalkane is you count how many other carbon atoms it's attached to, it's directly attached to. So it's attached to 1 carbon here, 2 and 3. So there are 3 carbon atoms directly attached to the carbon that's attached to the halogen, and that makes it a tertiary halogenoalkane. So you can see from the equation that the same type of reaction happens. So when we do hydrolysis of tertiary halogenoalkanes, the halogen is still substituted by the hydroxide ion, and what we produce is the corresponding alcohol, and the halide ion is chucked out. So we get the same products, but the reaction proceeds by a different mechanism. This time the mechanism is called SN1. So it's still S for substitution, N for nucleophilic, but the 1 this time stands for unimolecular. So it's still nucleophilic substitution, but this time the rate determining step only depends on the concentration of the tertiary halogenoalkane. The nucleophile, we'll see, is not actually involved in the rate determining step, in the slow step. So you can see, therefore, the rate equation only involves the halogenoalkane and not the nucleophile. K is just the rate constant. Again, you'll look more into that next year. And as it turns out, SN1 reactions are actually 2-step mechanisms. We saw previously that SN2 reactions were single-step mechanisms. So let's have a wee look at the mechanism and see how that is true. So in this mechanism, start off by just drawing your halogenoalkane molecule, which is 2-bromo-2-methylpropane. I've just drawn it in a square planar type shape, and it's just a little bit easier because we're going to be showing movement of electrons within this, as we do in each mechanism, but we're going to see how these alkyl groups donate electron density towards that central carbon, and that's a wee bit easier to show if our bonds are just straight lines. So it's okay with this one to show your mechanism just with straight lines as opposed to the tetrahedral shape around that central carbon atom. So there's our overall halogenoalkane, and you can see that it is a tertiary halogenoalkane. So we'll write that underneath. It's a tertiary halogenoalkane. Okay, and the other thing we want to draw on our mechanism is our partial charges. So our carbon is delta positive, our bromine is delta negative. So what actually happens in this mechanism and what makes it different is because of these alkyl groups, don't necessarily circle these in your mechanism, but these alkyl groups will be able to donate electron density towards that central carbon. You can see that it is slightly positive, and if you remember back to alkenes, and when we were deciding with an unsymmetrical alkene which carbon the hydrogen added to and which, say, the chloride ion added to, we said that alkyl groups can stabilise positive charge. Why can they do that? Well, it's because they can donate electron density towards this central carbon. And what that does is it both stabilises the delta positive charge, or if it was a carbocation, it would stabilise it. But as they donate electron density towards that carbon, it essentially pushes the electrons in the carbon-bromine bond even further towards bromine to the point where this breaks. So if you imagine a pair of electrons, which you can draw in that, if you wish, you don't have to draw that pair of electrons, but if you can try and imagine, I know they're not moving, so it's hard to visualise, but as the methyl groups donate electron density towards that central carbon, these electrons here are pushed closer and closer to your bromine, which then ultimately causes that carbon-bromine bond to break. So actually, before we even introduce the nucleophile, that carbon-bromine bond breaks, and that results in a full carbocation being formed, which will then be stabilised by the methyl groups. So before we introduce the nucleophile, the carbon-bromine bond actually breaks before it's introduced because of these alkyl groups, which are donating electron density towards the central carbon. In this particular mechanism, this is the slow step, and so therefore this is the rate determining step. And you can see that the nucleophile is nowhere to be seen. The nucleophile only involves the tertiary halogenoalkane, and that's why it's called SN1. And that's just described for you down here underneath stage 1. So only one molecule is involved in the slow step, and therefore it's unimolecular, and that's where we get this idea of SN1. So let's go on and show how the reaction proceeds. What I'm going to do here, now while it's not involved, I'm going to draw the hydroxide ion just in the first step. The reason really is to make sure the charge is balanced at each stage of the mechanism. Otherwise, if we only introduce it at stage 2, then stage 1 has no overall charge, and stage 2 will have a negative charge overall, so that will not be balanced. I'm going to draw it there, but you can see that's not affecting the fact that only the tertiary halogenoalkane is involved in the first step, because you can see there's no arrows coming from the hydroxide ion. It's not actually getting involved. So what do we produce in stage 2? Well, what we've got first of all is what's left of our halogenoalkane. So it's just essentially a carbon chain now. It's lost the bromide ion, and we'll draw the bromide ion before we forget about it. So we can just show it here, usually with its lone pair of electrons that it would have got from the carbon-bromine bond originally. And because carbon has lost an electron overall, it has a positive charge on it. It is now a carbocation, but again, it is stabilised by these alkyl groups, which are donating electron density towards that carbocation, stabilising it, which allows the reaction to proceed in this way. So now let's introduce our hydroxide ion, which is our nucleophile. So we can draw that really anywhere. I'll draw it here since I have a wee bit of space. I've written my positive charge of my carbocation on the other side, but really it can be shown coming from anywhere. This will really be a trigonal planar shape at this stage, so it can attack from like in front, behind, the side, wherever. And you can see now why we wrote the hydroxide ion in the first stage, to make sure the charges were balanced at each stage of the mechanism. In the first step, we just had our hydroxide, which was negative, so the charge was -1. And here we have our bromide ion, but that charge is cancelled out by the carbocation essentially, and then the hydroxide ion, which brings the charge to -1 again. So what we show here is this stage of the reaction is really reactive. You've got your carbocation positively charged, and your negative hydroxide ion, which is negatively charged. And so it goes in, it's attracted to the carbocation and forms a bond with it. Carbon's got 3 bonds at the minute, it wants 4. So the hydroxide ion easily moves in at this stage, uses its lone pair of electrons to form a bond with the carbon. What do we get as a result then? Well, the way I've kind of drawn it, I'll draw my hydroxide ion on the left of the molecule, but again, it doesn't overly matter because of the symmetry in the molecule. And we'll show our OH group here. And we'll also need to show our bromide ion again, just to make sure the charges are balanced at each stage of the mechanism. But again, it's just off to the side. It's not involved at this stage. So what have we produced? Well, this is a tertiary alcohol. If you wanted to write its name, we haven't done naming alcohols yet, but it's named as an alcohol as opposed to the OH group being a substituent. So the only substituent would be methyl, so it would be 2-methyl propan 2-ol, because the OH group, which is your alcohol group, is on carbon number 2, so that's why it's called propan 2-ol. So let's run through that mechanism one more time. So this proceeds in a different way. This is called SN1 because the nucleophile is not involved in step 1. There's only one molecule involved in the rate determining step, and that's the halogenoalkane. So that's the slow step, and what happens is the alkyl groups donate electron density down towards that central carbon, which causes the carbon-bromine bond to break, and then those alkyl groups can stabilise the resulting carbocation. In stage 2, then we see our carbocation, and that is then ready to react with our nucleophile. This stage 2 is very quick, so this is not a rate determining step. So even though the hydroxide ion, the nucleophile is now involved, this stage is quick, so it's not a rate determining step. So that hydroxide ion uses its lone pair of electrons to form a bond with the carbocation, and the resulting tertiary alcohol is then produced. So you can see this type of mechanism, which is SN1, involves two very separate steps. So stage 1, something happens, the bromide ion leaves, and then the hydroxide ion comes in a separate step. So there's two separate steps here rather than these things happening simultaneously. So two separate steps. And then, so therefore we call it a two-step mechanism, rather than a single step mechanism, which we saw with our SN2 reaction. So remember, the number refers to how many molecules are involved in the rate determining step, not how many steps there are, because actually with SN2 we see there's one step, and SN1 we actually see that there's two steps, as we've seen here. So in SN2, where that change happened simultaneously, the hydroxide ion formed a bond, the bromide ion broke a bond. Here we see that the carbon-bromine bond breaks first, and then in a separate step, the hydroxide ion comes in and forms a bond. So this is a two-step mechanism. Again, take a bit of time and practice drawing this out. You could even draw it into your revision sheet at this stage, your SN1 and your SN2 that we have met now. Just make sure you get them the right way around. Primary halogenoalkanes are SN2 and tertiary halogenoalkanes are SN1. But have a little look at that, see if you can draw that out for yourself. And just noticing here it says in stage 3 the alcohol is formed, and it should say the bromide ion leaves. If it was a chloroalkane, as our halogenoalkane, it would be a chloride ion that leaves, but in our example it's a bromide ion. So if you want to change that. Over on page 25, there's a summary of the SN1 mechanism, which you can have a read through. And then there's a summary box to just compare the hydrolysis of a primary halogenoalkane with the hydrolysis of a tertiary halogenoalkane. So first of all, let's talk about the product that is produced. With the hydrolysis of primary halogenoalkanes, the corresponding primary alcohol is produced. With tertiary halogenoalkanes, it's the corresponding tertiary alcohol that is produced. So both produce the corresponding alcohol, which will have the same structure as the halogenoalkane that it came from. So if it started as a primary halogenoalkane, it will end up as a primary alcohol, and so on. The particular type of mechanism which it proceeds by, for primary halogenoalkanes, it's SN2. Remember that 2 just represents that both the halogenoalkane and the nucleophile are involved in the rate determining steps. So it's what we call bimolecular, so we call it SN2. With tertiary halogenoalkanes, it's SN1 because there's only one molecule involved in the rate determining step. That's the halogenoalkane, so it loses the halide ion first of all before then reacting with the hydroxide ion. Then in terms of the mechanism and how many steps are involved, especially in that rate determining step, the hydrolysis of a primary halogenoalkane, it's a one-step mechanism, so the nucleophile forms a bond with the carbon at the same time as the halide bond is broken. With tertiary halogenoalkanes, it's a two-step mechanism. So as we said, the carbon halide bond is broken first, so the halide ion leaves first of all, and then the hydroxide ion comes in a separate step. So that's a two-step mechanism. So both proceed by nucleophilic substitution, but as we have seen, the exact mechanism is slightly different depending on whether it's a primary or tertiary halogenoalkane. Now, just to note, obviously there are secondary halogenoalkanes as well. And both types of mechanism can occur with secondary halogenoalkanes, as it says at the bottom of page 25 here. And it really just depends on the size of the alkyl groups attached to the central carbon. That's the carbon attached to the halogen. So remember, a secondary halogenoalkane will have two alkyl groups or two carbon atoms directly attached to the carbon that's attached to the halogen. So there's the carbon attached to the halogen, and it's going to have a total of 4 bonds. So 2 of those bonds will be to carbon atoms, and then 1 will be just to a hydrogen. So it really depends how big, how bulky these alkyl groups are, and how able they are to donate electron density towards the central carbon. And so if they are maybe big and bulky and good at electron donating, then it would proceed by SN1, similar to our tertiary halogenoalkanes. But if they're maybe smaller alkyl groups, not good at electron donating, then it will proceed more by SN2. But you wouldn't have to determine that in an exam or anything like that. They would focus on either a primary or a tertiary halogenoalkane. So you need to be confident with the differences between the mechanisms for primary and tertiary halogenoalkanes. So between SN2 and SN1, you need to be able to draw the mechanism for each of those. And what I would suggest that you do now is to pause now, or even at the end of this video. We've just one more little bit to do in this video, but make sure that you fill out that revision page that we did in school together of your summary of your mechanisms at AS. There's 2 more that you can fill in now, your SN2 and your SN1, and you can just pick, you can just copy the ones that we've done from our notes, or you can pick a slightly different halogenoalkane to start off with if you prefer. But draw those mechanisms in to start completing that revision page. So in the last part of this video, we're just going to look at comparing the rates of hydrolysis of different halogenoalkanes depending on what the halogen group is on your halogenoalkane. It's 2.5.7 on your specification. And we're really looking here at how quickly these hydrolysis reactions happen depending on what halogen group is attached to our halogenoalkane. So the rate of a chloroalkane with a bromoalkane compared with an iodoalkane. So what we're really doing is I've chosen just a random halogenoalkane of chloroethane versus bromoethane versus iodoethane. So if we were to keep the carbon length the same, which would happen fastest, which hydrolysis would happen fastest. So what we're comparing is the rate of this hydroxide ion coming into the chloroethane and chucking out the chloride ion, versus the hydroxide ion coming in on the bromoethane and chucking out the bromide ion, versus the hydroxide ion coming in and the iodide ion will be kicked out. So in terms of how fast this happens in comparison with these 3 halide ions, depends on 2 things. It depends on the polarity of the bond and the strength of the bond, and we're referring to the carbon-halogen bond. So how does bond polarity play a part in it? If you think about the carbon-halogen bond, the carbon is delta positive and the halogen is delta negative. But what we know about the halogens is that the electronegativity decreases as we go down the group. We know that fluorine is the most electronegative atom on the periodic table. So as we go down the group, the electronegativity decreases. So there's going to be a difference in electronegativity depending on the halogen that is bonded to the carbon. So the more electronegative the halogen is, the more polar the carbon halogen bond will be. And the more polar that bond, then essentially the carbon atom will be more electron deficient, in other words, more delta positive. And therefore, if it's more delta positive, think about what's trying to happen here in nucleophilic substitution. The halogen is trying to attract a nucleophile, and a nucleophile is attracted to regions of low electron density, in other words, areas that are delta positive. So if you've got the carbon being more delta positive, then the nucleophile is attracted more easily. So the more polar the bond is. Carbon's more electron deficient, which attracts the nucleophile more easily. In other words, we would expect this particular halogenoalkane, the more polar the bond is, to undergo hydrolysis more quickly. So if we were just looking at bond polarity, we can see that the difference in electronegativity between carbon and chlorine is 0.5. The difference in electronegativity between carbon and bromine is 0.3. And the difference between carbon and iodine is actually 0.0. And they have the same electronegativity. That means if we were to compare the polarity of these bonds, we can see that the carbon-chlorine bond is the most polar. So we could almost represent that as saying carbon is delta plus plus, and the chlorine is delta negative negative. So there's a bigger difference in electronegativity there. You don't have to draw that on the bond if you were doing chlorine, but it has the biggest difference in electronegativity out of these three. Carbon and bromine, the bond would still be polar, but in fact the carbon iodine bond overall is actually non-polar. There is no difference in in electronegativity, so that bond is not polar. So if we were just looking at bond polarity, we would expect the hydrolysis of chloroalkanes to happen the fastest, because that's the most polar bond. So the carbon is the most electron deficient, the most delta positive, and so the nucleophile we would expect to be attracted more easily. But there's another factor at play as well, because we don't just have to attract our nucleophile, we also have to break the carbon halogen bond as well. So if we're thinking of bond strength, we're thinking that the weaker the carbon halogen bond is in the halogenoalkane molecule to start with, then the faster this will happen. The weaker that bond is, then it's easier to break. And we want it to break because we want the hydroxide ion to come in and the halide ion to leave. So the weaker that bond is, the easier it is to break. And the halogen is what we call a better leaving group. It leaves more easily, it leaves more readily. And what we find as we go down the group of halogens, you can see the carbon-chlorine bond has a bond enthalpy of 327 kilojoules per mole. Carbon-bromine bond is 209, and the carbon-iodine bond is 200. So as we go down, that bond is becoming weaker. So the weakest bond out of the three is the carbon iodine, followed by carbon bromine, followed by carbon chlorine. And that's also reflected in the bond length as well. You can see that as we go down the group, and this will be a factor of size of the halogen as well, but also the strength of the bond. The bond is getting longer. In other words, it's getting weaker. So note the longer the bond, the weaker the bond is. So what is the overriding factor? Is it bond polarity or is it bond strength? Well, we can actually investigate this experimentally, which we'll talk about in a second. But what investigating it experimentally shows is that an iodoalkane is the fastest to undergo hydrolysis, followed by bromoalkanes, followed by chloroalkanes. Yes, the carbon-chlorine bond is the most polar and therefore will be the most open to nucleophilic attack by our hydroxide ions. But the carbon-chlorine bond is stronger than carbon-bromine bond, and as a result, the chlorine doesn't break off easily and the hydrolysis reaction is quite slow. The carbon-iodine bond, yes, it is not polar overall, but it is the weakest. So though it can't attract hydroxide ions very well, when it does, the iodide ion can break away very easily, and as a result, iodoalkanes hydrolyze the quickest, followed by bromoalkanes, followed by chloroalkanes. And so what does that mean overall? Well, it means the factor of bond strength is more important than the factor of bond polarity. So bond strength trumps bond polarity. What we mean by that is the fact that the carbon halogen bond gets weaker as we go down the group of halogens. That has a bigger impact on the rate of hydrolysis. And so we see iodoalkanes are most prone to hydrolysis, followed by bromoalkanes, followed by chloroalkanes. So how do we prove this? How do we test this experimentally? Well, essentially we're doing our hydrolysis reaction, and then we're also adding in some silver nitrate solution, and that is our test for halide ions. If you remember back to your qualitative tests, you know that silver nitrate reacts with halide ions to produce precipitates. So white precipitate for chloride ions, cream precipitate with bromide ions, and a yellow precipitate with iodide ions. So how we do this is we place a small amount of our halogenoalkane in a separate test tube. So you would use the corresponding halogenoalkane. So if you start with, say, chlorobutane, you would use bromobutane and iodobutane. You add ethanol to each test tube to act as a mutual solvent, and then add your silver nitrate solution. You place the test tubes in a hot water bath, and you warm to the same temperature. And you record how long it takes for a precipitate of this silver halide, so your white, your cream, or your yellow precipitate. So there's two reactions happening here. First of all, our hydrolysis, where our halide ion is replaced by our hydroxide ion. And then second of all, the halide ion that is essentially liberated would go on and react with an ion of silver from our silver nitrate solution to produce our precipitate. So that will be our precipitate. And so the faster that precipitate forms means that the halide ion has been produced quicker, which means that it's been liberated from the original halogenoalkane quicker. In other words, hydrolysis has happened more quickly. So the more quickly the hydrolysis reaction happens, the more quickly the halide ions will be produced, which will then go on and react with the silver nitrate to produce your precipitate. So if the results are what we expect them to be from our theory in the previous page, then we would expect a yellow precipitate of silver iodide to form first, followed by a cream precipitate of silver bromide, followed by a white precipitate of silver chloride. So what I'm going to do now is show you this reaction, and in school we actually only had a bromo and iodo alkane, so I couldn't compare it with the chloro, but you will see the difference between the bromo and the iodo alkane. Apologies that the sound is not great, because I had to keep the fume cupboard, the fan on in the fume cupboard, so it's quite difficult to hear me talking over it, but hopefully you'll see the results anyway. And then on Teams, I've also uploaded the link to the SIA website where they demonstrate this reaction. It's actually Miss Stewart again recording that video for the SIA practical videos online, so you can have a watch at that as well after this next video. So in this reaction, I'm going to test the relative rates of hydrolysis of our halogenoalkanes. Unfortunately, we don't have any chloro alkane, but we do have bromobutane, and we have iodobutane. So we're going to keep them the same chain length, but just changing the halogen atom. So the first thing I'm going to do is measure in a small amount of our bromobutane and put it in the first test tube. So just about 1 centimetre cubed. Next in, I'm going to put about 2 centimetres cubed of ethanol, and that just acts as a neutral solvent to dissolve the solutions that we're using and get them to react and mix well together. So about 2 centimetres cubed of ethanol in our bromobutane, and the same in our iodobutane. And then what I'm going to do is I'm going to add in our silver nitrate solution. That will cause a precipitate of our silver halide to form, and again add about 2 centimetres cubed of that to each. It starts as a colourless solution, silver iodide. You can see with our test tube that it contained bromobutane. Nothing is formed just yet. And if we want, we can time this to get the exact time, but you can see that the precipitate with our iodoalkane has formed much quicker than with the bromo. We're starting to see a bit of a precipitate at the top of the first test tube with our original bromobutane here. You can see there at the top there's a bit of cream precipitate. We'll leave that in a bit longer to see if we can see any more. And if we were to compare this with chlorobutane as well, that precipitate, the white precipitate of silver chloride, would take even longer to form. So you can see, hopefully, in the test tube that has the bromobutane in it, we're starting to see a precipitate forming here, a cream precipitate you can see up at the top of the test tube, and that's a precipitate of silver bromide, but it's forming much more slowly than the precipitate of silver iodide. So there you can see the two precipitates. The cream precipitate of silver bromide on the left, the yellow precipitate of silver iodide on the right, and the yellow precipitate of silver iodide was formed much more quickly. So as I said, you can also watch Sia's practical video on this, which I've included the link of on Teams. You can watch that video of that same reaction, which also compares the chloroalkane. So that completes this section on the nucleophilic substitution of halogenoalkanes. I know that's quite a long video and a lot to that, as we looked at the difference between SN1 and SN2 of our primary halogenoalkanes and our tertiary halogenoalkanes as well. We looked at the slight differences between those two mechanisms and how to compare the rate of hydrolysis of halogenoalkanes depending on whether they're a chloro, bromo or iodoalkane. So that's one of the most major reactions of halogenoalkanes, and we just have one more reaction to look at, which is elimination reactions of halogenoalkanes, which we'll complete in our next video. So what I'd encourage you to do, if you haven't already done so, is to fill in the SN2 and the SN1 mechanisms on the revision sheet that I gave you in school. So on that A3 summary sheet of the mechanisms that we meet this year, I'd encourage you to fill in those SN2 and SN1 mechanisms, and then you'll just have the elimination mechanism to complete after the next video.